Hello everyone, and welcome to this video for 10.5, looking at area and arc length in polar coordinates. The objectives for this video are: number 1, find the area of a region bounded by a polar curve. Number 2, find the points of intersection of two polar curves. Number 3, find the arc length of a polar curve. And number 4, find the area of a surface of revolution in polar form. Okay, now to identify the area of a polar region, what we're going to do is do something very similar to what we did when we dealt with the area between a curve and the x-axis. And we're going to break that up into pieces and we're going to approximate it. But the difference is, where before we used rectangles to approximate it, in this case, to go through and approximate this area, we're going to use sectors. And you might recall from pre-calc that the area of a sector is 1/2 times the radius squared times theta. So what we're going to do is we're going to look at this. We have a curve here, this polar curve right here in black. That is the equation for that is r equals f of theta. F is some function of theta. But what we want to do is we want to find the area. We have alpha drawn here and beta drawn. We want to find this area between these two, between the curve and this polar axis. So I want to find the area of that region. So what I'm going to do is I'm going to take this and I'm going to break that up into pieces. I'm just going to draw some radial segments that are going to start from the pole here and come out. We're going to hit that curve at different spots. I'll just draw a couple of them here. Just go with that. And then what I can do with this is I can use sectors. So I'll call this theta 1. There's theta 2, theta 3. And so I'm going to go through, I can go through and think of this as a sector here, drawing like that. And then we go through until I have a different sector. And so now when I take a look, like if I look at this first sector, okay, then what I know is that that area 1, is going to be 1/2 times, my radius for that is f of theta 1, that thing squared, times, we'll just call it, we'll say this is a regular partition, so it'll just be delta theta. And then area 2, I'm going to go through, the radius of area 2 is going to be the value at theta 2, so it's 1/2 times f of theta 2, that thing squared, delta theta, and so forth. And so what I can do with this is I can take these, add them up, and I can say that that the sum of my areas, area 2 plus dot dot dot, is going to be 1/2 times the sum as n equals 1 to k of f of theta sub n, that thing squared, times delta theta. And if I do that, so as k gets larger and larger, and what ends up happening again is as k gets larger, in other words, as my delta theta start approaching 0, getting smaller and smaller, getting closer to 0, this thing just becomes 1/2 times the integral from alpha to beta of f of theta, that thing squared, d theta. Or looking at more formally, what I have is if f is continuous and non-negative on the interval from alpha to beta, and 0 is less than beta minus alpha, so the beta minus alpha is between 0 and 2 pi, then the area of the region bounded by r equals f of theta between the radial lines, theta equals alpha and theta equals beta, is a equals 1/2 times the integral from alpha to beta of f of theta squared d theta, or if you want to, 1/2 times the integral from alpha to beta of r squared d theta. Now let's look at an example. In this case, I have the graph of r equals 3 cosine of 3 theta, and I'm asked to find the area of one leaf of this three-petaled rose. So what I have to do is identify angles that go between this. Also, remember, we want my function values to be non-negative. So in this case, what I have is I know that at 0, I am here, and that as I go over here to this point, as I travel along this curve, it's going to be at the back at the pole at pi over 6. So one of the things I have in this case is I know that if I have the line at pi over 6, that's going to be one bound that I can have. And then if I go in the other direction here, if you remember in terms of graphing these, one of the things that we found is that when we go here, this would be, as I work my way back, I'd be at 11 pi over 6, which would also be negative pi over 6. So if I draw in this spoke right here, that's going to be at negative pi over 6. So in this case, I can set up an integral to find the area of that leaf. I could just say it's going to be 1/2 times the integral from negative pi over 6 to pi over 6 of 3 cosine 3 theta, that thing squared, d theta. Now I do have to go through and multiply that out. So that is going to that'll end up being 9 cosine squared of 3 theta. So I'm going to pull the 9 out. So that'll be 9 over 2 times the integral from negative pi over 6 to pi over 6 of cosine squared 3 theta d theta. Now at this point, we're going to need to remember something because we're now into a trig integral. So if I want to go through and do that, I need to remember that cosine squared theta is equal to 1 plus the cosine of 2 theta all over 2. And so in this case, this is going to be now 9 over 2 times the integral from negative pi over 6 to pi over 6 of 1 plus the cosine of 6 theta all over 2 d theta, or pulling the 1/2 out, I have 9 over 4 times the integral from negative pi over 6 to pi over 6 of 1 plus the cosine of 6 theta d theta. And now we have to integrate that. So when I take that antiderivative, the antiderivative on that one, it's going to come out to be 9 over 4 times, that will be theta plus 1/6 sine 6 theta. And in this case, I'm going to go from negative pi over 6 to pi over 6. So for that, it's going to be 9 over 4 times, when I plug in pi over 6, I will get pi over 6. When I plug pi over 6 in there, it's going to be 0 minus, when I put in a negative pi over 6, I'll get negative pi over 6 there, and again plus 0. So the result then on this is that I'm going to end up with that being 9 over 4 times pi over 6 minus a negative pi over 6 is going to be 2 pi over 6, or pi over 3. So I get 9 pi over 12. So the area of one leaf is going to be 9 pi over 12. Now that's one way to do it. I could have also gone through on this one. I could have said originally that I know that there's symmetry here, so I can say from 0 to pi over 6, if I just double that, that's going to be, so if I found the area from 0 to pi over 6, just that portion, it would cover this much right there. I double it, it would also give me the area of one leaf as well. Now here's another problem where when we're asked to go through and find the area of the region between r equals 2 minus 2 cosine theta and r equals negative 6 cosine theta. So really what we're looking at here is we're looking at this region right here. And on this one, we're going to use that same idea what we just talked about. We're just going to focus on finding this top part, and then we can double that. Okay, so the first thing we're going to have to do is identify the intersection points. Now this is where it's going to be important for you to graph it. I want you to notice something on this. We have 3 points here that they have together, don't they? Okay, so when we look at this though, this will come out to be at theta equals 2 pi over 3 and 4 pi over 3. And so those points right there are located here and here. So I have a segment that, if I draw a line that comes out here, there's 2 pi over 3. And then here is 4 pi over 3. And that's 2 pi over 3. So what happens on this thing? So in this case, I now have 2 regions I've got to work with. I have a region that is right here, that region, that's part of this, the whole thing between the 2 curves. And then I have another region that I'm going to be looking at, which is this one right there. Okay, so I have those 2. So I'm going to want to set this up. Now, you notice here that we didn't get this one. Part of the reason we didn't get that one, though, is also because of the fact that they're different thetas. In this case, if you notice up here, graphically, when I put, this is at the pole, this is going to be at the pole when theta equals 0. Because if I put 0 and cosine of 0 is 1, so I get 2 minus 2, which would be 0. This one, when I put 0 in for this one, I'm out at negative 6. I am at the pole on this one at pi over 2. So now in this case, when I'm looking at this, so the first one, the circle in red is negative 6 cosine of theta. Now that one, that portion, this portion right there is going to be found by integrating this function, negative 6 cosine of theta, finding the area between that curve and the region there is going to be from theta equals pi over 2 to theta equals 2 pi over 3, but we're going to be working with just this curve. The remaining area here is a sector from 2 minus 2 cosine 2 theta. So, and that's going to go from 2 pi over 3 all the way over here, which that's going to happen when theta is equal to pi. Because if I put that's out at 4, this will be equal to 4 when theta is equal to pi, because cosine of pi is negative 1. So now remember, in this case, we want the full area of the curve, between that curve and the and with theta in that between the 2 curves where it's 2 pi over 3 and 4 pi over 3. So to do this, though, I decided to go through and split it in half. So I'm going to just go from pi over 2 to 2 pi over 3 for that first region, which we talked about for this circle, and then the 2 pi over 3 to pi for the second region bounded by that cardioid that we had 2 minus 2 cosine squared theta. So a over 2 in this case is 1/2 times the integral from pi over 2 to 2 pi over 3 of negative 6 cosine of theta squared d theta. And to that we're going to add the area of that sector, which is 1/2 times the integral from 2 pi over 3 to pi of 2 minus 2 cosine theta, that thing squared d theta. At this point, it's algebra. So I squared the cosine, negative 6 cosine of theta, and I squared the other function, 2 minus 2 cosine theta, and I got these. I pulled out the 36 to make that 18 times the cosine squared of squared theta d theta. And this one right here, you'll notice I lost the 1/2, and that's because I pulled out a factor of 2. Okay, pulled out a factor of 2. Now I could have pulled out a 4, but I have a reason why. If you take a look down here, why I might want to keep that not pull out the whole factor of 4. So I have that at this point. Now I do have to go through again. We're dealing with trig integrals, so I have to use the power reducing formula. I know cosine squared theta is 1 plus the cosine of 2 theta over 2. And same thing here. This one at this point here, These 2's will cancel each other out, so that will be gone. So I have 2 minus 4 cosine theta plus 1. Well, 2 plus 1 will give me that 3 that's right there, minus 4 cosine theta plus cosine of 2 theta, d theta. And in this case right here, I pulled out this 1/2 again, so that 1/2 came out, that gave me 9. So I have 9 times the integral from pi over 2 to 2 pi over 3 of 1 plus the cosine of 2 theta d theta plus 2 pi over 3 to pi of 3 minus 4 cosine theta plus cosine of 2 theta d theta. When I integrate that, the integral of 1 d theta is going to be theta. The integral of cosine 2 theta is going to be 1/2 sine 2 theta. And so I'm going to plug in 2 pi over 3 and pi over 2 in there. The integral over here is going to be 3 theta minus 4 sine theta plus 1/2 sine 2 theta, and again from 2 pi over 3 to pi. When I plug 2 pi over 3 into this, I'll get 2 pi over 3 minus the square root of 3 over 4 minus what I get when I plug pi over 2. When I plug pi over 2, I'll get pi over 2 there, but this will be the sine of pi, so that's why it's just, the sine of pi is 0, so that's why we just have the pi over 2 when I did that. Over here, when I plug in pi, I'll get 3 pi, but when I plug pi into each of these two, that's going to give me sine of pi, sine of 2 pi, both of those are 0, so I just have the 3 pi, minus what happens when I put 2 pi over 3 in. Well, 2 pi over 3 times 3 is going to give me the 2 pi. Sine of 2 pi over 3 is going to be square root of 3 over 2, so that gives me the negative 2 square root of 3. And then when I plug the 2 pi over 3 in there, that's 4 pi over 3, which is now going to be a negative square root of 3 over 2 times 1/2, so I get negative square root of 3 over 4. At this point now, I distribute the 9. So when I take 9 times 2 pi over 3, I get 6 pi. And then 9 times the square root of 3 over 4 gives me minus 9 square root of 3 over 4. And then minus 9 pi over 2 plus 3 pi minus 2 pi. Now, what I did here, I wanted to get, I know I'm going to have to deal with 9 square root of 3 over 4, so I just got the common denominator. So that's going to, that'll be a minus a negative, would be plus 2 times the square root of 3. But if I put that over the 4, I get 8 square root of 3 over 4, and that's going to be plus square root of 3 over 4. Well, at this point, again, I look at it, 8 pi over 4, 8 square root of 3 over 4 plus square root of 3 over 4 is 9 square root of 3 over 4 minus 9 square root of 3 over 4. So those drop off. So I'm left now with the 6 pi minus 9 pi over 2 plus 3 pi minus 2 pi, which ultimately ends up as being 5 pi over 2. So in this case, a over 2, you have to remember at this point, a over 2 is equal to 5 pi over 2. So the answer on this one, the answer for A, comes out to be 5 pi square units. Because remember, in that graph, we were just looking at that top portion, but we needed to double it to get the whole region that we were looking for. The next one we're going to look at is the arc length of a polar curve. And again, it comes from the parametric version. And remember, so in that case, x is f of theta cosine theta. Y is f of theta sine theta. And so if I'm going to use the parametric version of that, I have to take the derivative and I simplify it. And I do all the simplification and everything. And ultimately, what it comes out to be is that under these conditions here, that the function's continuous and the derivative is continuous on the interval from alpha to beta, then we go through and we can say that the arc length, S, is equal to the integral from alpha to beta of the square root of f of theta, that thing squared, plus f prime of theta, that thing squared d theta. Or, if you prefer, S equals the integral from alpha to beta of the square root of r squared plus dr d theta, that thing squared. Let's take a look at an example. So in this case, I do have a circle. This is the graph of r is equal 4 sine of theta. And I'm going to look at this from 0 to pi. Okay, so we want the arc length. Well, right now, at this point in time, I'm fairly certain you can all go through and calculate what that arc length is, just because you know how to calculate the circumference. 0 to pi means we're going to actually just be taking half of that circle. So in this case, the arc length that we're looking at when I go from 0 to pi on this is going to be this portion right there, that half of that circle. So the way I set it up is I said r equals 4 sine theta, dr d theta is 4 cosine theta. So my arc length s is going to be the integral from 0 to pi of the square root of 4 sine of theta, that thing squared, plus 4 cosine of theta, that thing squared, d theta, which equals the square root of 16 sine squared theta plus 16 cosine squared theta, d theta, where I pull out the 16, and I forgot that parenthesis, but we'll put it in there. There. I get 16 times sine squared plus cosine squared, which we know is 1. And so that's whole square root. This whole entire square root just simplifies to be 4. So we now have the integral from 0 to pi of 4 d theta, which is going to be 4 theta. And when I do that, that will end up equaling 4 pi minus 0. So I ultimately get that 4 pi as my answer. Now let's take a look at what happens when we're dealing with the area of a surface of revolution. Now in this case, when we talk about these surfaces, like we did with the parametric, we're not going to be able to, when we dealt with the surface area and arc length and so forth, the surface area from before, at the beginning of the year, in chapter 7, we could go through and change that axis that we were rotating. We didn't have to rotate around the x-axis or y-axis. We could rotate around x equals 3 if I wanted to. Well, in this case, like we did with the parametrics, we're only going to be rotating around one of two lines. Now, in the parametrics, we still had the x-axis or y-axis. In terms of the polar coordinate system, we don't have an x-axis and y-axis when we look at it. We have what's called the polar axis, which the polar axis is basically at that x-axis spot, and the vertical axis is theta equals pi over 2. So that would be like the y-axis. And so when I set that up again, remember it's area, the surface area was 2 pi times the radius times the arc length. Well, you'll notice in this case, there's our arc length, there's our 2 pi, the radius. The radius when we're going around the polar axis is, if you think about it, it would be, if we converted it into x and y coordinates, it'd be like y. And so that's why we have f of theta sine of theta. We're going around the polar axis. And we go around the line theta equals pi over 2. I have f of theta times the cosine of theta times that square root. Now, let's take a look at an example. We'll set it up. So in this case right here, we have r equals 4 cosine of 2 theta. And I'm going to take the interval from 0 to pi over 4. I'm going to take that region, that portion of the curve, and I'm going to rotate it around the polar axis. Well, the first thing I do is I find the r prime, the derivative of that is going to be negative 8 sine of the 2 theta, which is dr d theta. So I plug that in. We're going around the polar axis, so it's going to be f of theta, r, times sine of theta. So it's s equals 2 pi times the integral from 0 to pi over 4 of 4 times the cosine of 2 theta times sine theta times the square root of 4 cosine 2 theta, that thing squared, minus 8 sine 2 theta, that thing squared, d theta. At this point, on this one is not, it would be one that you would end up putting into your calculator. Thus why we only take it to a certain point and we finish it. But I did try simplifying it some just to make it a little bit easier to plug into the calculator. So the first thing I did here, I pulled the 4 out. So I have 8 pi times cosine 2 theta times sine theta times the square root of 16 cosine squared 2 theta plus 64 sine squared 2 theta. I did pull out a factor of 16, which when I pull that out, that's a 4 going to be 4 on the outside, thus 32 pi times the integral from 0 to 2 pi to pi over 4 of cosine 2 theta sine theta times the square root of cosine squared 2 theta plus the 4 sine squared 2 theta. I just broke that up as sine squared 2 theta plus 3 sine squared 2 theta. Cosine squared plus sine squared is 1. So ultimately I have it down to this, which is a little bit easier to plug in. Oh, I forgot my pi, didn't I? So let me put that pi in here. There we go. So I have 32 pi times the integral from 0 to pi over 4 of cosine 2 theta sine theta times the square root of 1 plus 3 sine squared theta d theta. I'd plug that into the calculator, and then I could get my answer on this particular problem, because it didn't simplify nice. So with that, this does end this video. I know it was quick. There's a lot of stuff there. You got the how to find the area, finding the intersection points we did in the problem where we had the 2 pi over 3 and 4 pi over 3, finding the area between the curves, and then also arc length and surface area by rotation. So there's a lot there, a lot to keep track of in terms of formulas, but I know you all can do it. So with that, hope you're having a good time, and we will talk to you later. If you have questions, do not hesitate to send me a message on Remind or on Classroom, either one. Okay? All right. Hopefully we see you soon, but be careful and stay safe.